This is Chapter 18, Section 1. We're going to talk about chemical equilibrium. Again, I might go through some of this stuff kind of fast. You make sure you get everything written down. If we need to skip over something that's not relevant for you to put in your notes, I'll let you know. So theoretically, every reaction can go in two directions, forward and reverse. A reversible reaction is a reaction in which the products can react to reform the reactants. In a reversible chemical reaction, the rate of its forward reaction equals the rate of the reverse reaction, and the concentration of the products and reactants remain unchanged. So the state of dynamic equilibrium has been reached when the amount of products and reactants remain constant, and both reactions will continue until there is no net change in the composition of the system. So the system can continue to move in the forward and reverse direction to keep making products and in turn keep making reactants to stay in this equilibrium phase. In this particular video, it would have shown you that the vapor pressure of a gas is equal to the pressure of the atmosphere. We did learn that earlier in a different chapter, but again, that is going to be a reminder here. This is showing you the chemical equation for the breakdown of mercury 2 oxide into its elements, mercury and oxygen gas, and that it is an overall reversible reaction. And notice the arrows moving in both directions to show you a reversible reaction. Many of these reactions do occur under ordinary conditions of temperature and concentration of your reactants and therefore your products. Once they reach a state of equilibrium, until at least one of the substances involved escapes or is removed from the reaction system. So if you all of a sudden pull some of the reactant away that you initially started with while this reversible reaction is going on, that changes the state of your system. When the products of the forward reaction are favored, there is a higher concentration of products than the reactants at equilibrium, so the equilibrium would lie to the right. So the same could be said of this last statement too. If the reactants in your reverse reaction are favored, then the equilibrium would lie to the left. And you'll see that on the next slide. So both forward and reverse reactions do occur nearly at the same extent before equilibrium is established, and neither reaction is favored, and considerable concentrations of both reactants and products are present at equilibrium, because again, this will continue to move in both directions. If the products of a forward reaction are favored, which means lies to the right, and in this example right here, you can see the reverse reaction, that arrow is slightly smaller, so sulfur dioxide and oxygen gas reacting to give you sulfur trioxide. You can see that the forward reaction here is going to be slightly favored. Notice also too that there are fewer moles in the forward direction, so if we were to look at our coefficients, 2 plus 1, that's 3, whereas we only have 2 over here being produced. In this next example, the reverse reaction is favored, so you've got carbonic acid and water that are producing the hydronium ion and the bicarbonate ion, and it shows you that the reverse reaction is favored here because your hydronium ion, your two ions want to combine as well to reproduce your carbonic acid and your water. In this one, we do basically have the same number of moles in both phases. So 1 plus 1, that's 2. 1 and 1, that is 2. And everything is in the aqueous or liquid phase here. So it could be a lot harder to tell which side would actually be favored. And in this one right here, truly reversible reaction, you got your sulfuric acid and water breaking down into the hydronium ion and the HSO3 minus ion there. And this one, neither side is going to be favored. So we have our equilibrium expression. We're going to eventually get into the equilibrium constant using this information. So your NM, your XY, those are going to be the moles of your reactants and products, your coefficients for a balanced reaction. The concentrations of C and D are 0, and those of A and B are going to be maximum. Over time, that rate of the forward reaction does decrease as A and B are used up. And then the rate of the reverse reaction increases as you produce more C and D. But as C and D are being produced more, then they're going to start to reverse to produce or break back down into more of your A and B. And the two reactions will occur at equal rates, so equilibrium will be established. Please get this in your notes. This just shows your reaction rate over time for an equilibrium system. You see your reaction rate there on the y-axis, and then you've got your time there on the x-axis, and it's showing you that the forward reaction, you have a lot of A and B here at the top. They start to react to give you C and D. And then you have no C and D to start with, so that's why it's there at 0. But as C and D are produced, you can see that their reaction rate starts to increase. And eventually you do hit an equilibrium position between the two, so the forward and reverse rates occur at equal rates. So looking back at that same expression, after we have reached equilibrium and your concentrations of A, B, C, and D can go no further because you're going to keep conditions the same, the ratio of their concentrations also remain constant, and we have a new constant that we're calling the equilibrium constant that will come into play, and we're going to use a capital K for it. So that equilibrium constant, it is the concentration of your products raised to their molar power divided by the concentration of your reactants raised to their molar power. Please make sure you get that in your notes. And again, it is products over reactants. And you can see how the coefficients X, Y, N, and M are used there to raise to a power. So our constant K will be independent of your initial concentrations, but K is dependent on the temperature of the system. So that equilibrium constant will change if temperature changes. The numerical value of K for a particular equilibrium system is obtained experimentally. So even though we're going to look at some values of K here in just a little bit, you don't need to write those down. It would either be given to you in a problem or you would have to solve for it experimentally and do a little bit of math. If K is equal to 1 at equilibrium, there are roughly equal concentrations of reactants and products. So again, that's if it's equal to 1. Looking at this, if the value of K is small, the reactants are favored. So if K is less than 1, then we're going to favor the reactants. If K is going to be greater than 1, then the products are going to be favored. Concentrations of substances that can actually change are included in K. So if you have a pure solid and liquid, they are omitted because their concentrations cannot change. So if you have a pure solid or a pure liquid, then you do not include their concentrations. And we'll look at some examples of what we're talking about there. So your steps, you'll write you a balanced chemical equation first. Then you'll write an equilibrium expression. And in the equilibrium expression, again, it's products in the numerator, reactants are going to be in the denominator. The concentration of any solid or pure liquid are omitted because they can't change. And for a reaction occurring in aqueous solution, water is omitted because, again, water is actually going to be considered a pure liquid. The concentration of water almost always stays constant during a reaction. And then we'll complete our equilibrium expression. You'll raise it to the proper powers that are needed. So this gives you the official definition for the equilibrium constant K, which we've already been explaining. And then K is sometimes referred to as the chemical equilibrium expression. Either way, we'll be talking about the same thing. Here are some values for equilibrium constants, and it gives you several reactions here and what their values are. Notice that they give them at different temperatures. So that K is dependent on temperature. So if you change the temperature, K will end up changing. Again, you don't have to get these specifically in your notes. It's just showing you some of the different workups that we have here. I will say, for instance, though, notice water here is put into this expression, but water is in its gas phase there, not its liquid phase. Water here in its liquid phase is left out because it is considered to be in its pure form at that point. And this gives you some other examples also. Just look through those. Again, you don't have to write them down, but it gives you an idea of how the expressions will be set up, and then typical K values that you're looking at different temperatures. We're going to look at the equilibrium expression between hydrogen iodine and hydroiodic acid. The rate of the reaction that we have here, and you'll get to see a graph too on the next slide. The rate of the reaction between our reactants, hydrogen and iodine, and a flask at an elevated temperature can be followed by observing the rate at which the violet color of the iodine vapor diminishes. So the color fades to a constant intensity, but does not disappear completely because the reaction is reversible. And hydrogen iodide decomposes to reform hydrogen and iodine. So you won't be able to see the hydrogen gas, but the iodine gas in its natural state there in the gas does have an iodine or violet color to it. So they're saying that this can actually be looked at visually too. This is what it's going to look like if you were to do the reaction rate graph, so reaction rate on your y-axis and time on the x. The forward reaction, hydrogen and iodine producing HI, and then you also see your reverse reaction, and they do reach an equilibrium point too between the forward and reverse reaction. Our net equation would look like this. And there's the equilibrium constant expression for it. Again, see how the coefficient 2 right here is being used to raise HI to the second power. And the value of K is a constant for this system at equilibrium at a particular temperature. Now we're going to look at some examples here. This goes with that system. You don't have to write this down, but it is just giving you an idea about the concentrations that you would have of your two reactants right here. So that's their molar concentration, or moles per liter. And then you have your product concentration right here. And it has actually put these values for the 4 different experiments into our equilibrium constant expression, and look, you get essentially a constant value for any of those 4 experiments as your reactants, their concentration is changing and your HI concentration is changing. And it looks like all of this is being shown. Let's see. It's going to say forward and reverse, but I am looking at those. This could just be looks like it's already at equilibrium, yeah. So be sure to get down this sample problem as we go. So an equilibrium mixture of nitrogen, oxygen, and nitrogen monoxide gases at 1500 Kelvin is determined to consist of, it's given you the concentration here. So that's going to be the concentration of nitrogen. Here is the concentration of oxygen, and there is the concentration of nitrogen monoxide. And it's asking you what is the equilibrium constant for the system at this temperature. So if we go ahead and we just work it out here on this particular one, we're going to set up K. You've got, let's go and do our balanced equation. I'm going to put that up here at the top. Nitrogen plus oxygen, both of those are gases yielding nitrogen monoxide. So our coefficient in this one, we would put a 2 right there to balance this equation. So when we go to write our constant expression, that is NO squared over N2 and O2. And you're ready to plug in your numbers. So 1.1 times 10 to the negative 5th, that is squared over 1.7 times 10 to the negative 3, and I think I've got these numbers backwards. That's actually oxygen's value, but since oxygen and nitrogen are both in the denominator, it will not matter. Times 10 to the negative 3, and they're multiplied. And when we look at this right here, get your calculator out, do a little bit of math. You will get 1.1 times 10 to the negative 5. And for this, if I'm looking at units, notice that our units there in the numerator, that would be molarity squared. This is molarity, molarity. Again, molarity is moles per liter. And all of these units do cancel. And that is your final answer.